a national, or rather has become an international event organized by the EPSRC NetworkPlus. And on this final day, we have especially dedicated this day for the ECRs, which have been the founding stone in our strategy of the network to boost the participation of early career researcher or investigators, particularly those who come from underrepresented communities or BAME origins, here what they call it as in the UK. So today's session is primarily dedicated to early career researchers, and that is a mix of both PhD students as well as those who already have completed their PhD but yet to take a permanent academic position. So in that spirit, today we have primarily three speakers planned for us. One is Mr. Avnish, who is pursuing his PhD with Professor Harpreet Singh, who presented about cold spray yesterday, or rather day before yesterday. We then have Vish presenting from LSPU, who is currently working with me on an EPSRC funded project. And we then have John Saputo, who is working with Professor Sanjay Sampath, who was our day one speaker of this event. So there are three very exciting talks on a mix of topics, which we are very keenly looking forward to. And we hope that these talks will stimulate some further discussions. There is another analogy here that, as we say in general for life, that usually what would happen is a life starts first with an experienced campaigner, which is what we had already first few days of thermal spray week, with experience reflecting on the history lessons, which we were very fortunate to visit into. And then towards the fag end of the life, we look forward to a newborn baby in a family. So likewise, ECRs today are actually going to show us what's new is happening in the area, or what the future is holding for us, that they're already actively working on. So it is expected that what is going to be seen today is going to drive the future of thermal spray, because the future will be held in the palms of ECRs. So on that note, Avnish, I would like to begin to welcome you. Mr. Avnish Kumar is a PhD research scholar in the Department of Mechanical Engineering at Indian Institute of Technology, shortly called as IIT, at Ropar in Punjab state in India. He's about to just submit his PhD thesis, which will be titled as Investigation on TI or titanium-based coatings for biomedical applications. He received his bachelor's degree in mechanical engineering from UPTU in India, and his master's degree in industrial tribology from National Institute of Technology, Srinagar, in the state of Jammu and Kashmir, or it used to be the state of Jammu and Kashmir, now a union territory. During his master's, he worked on tribological behavior of copper nanofluids in EHL line contacts, and his research interest includes surface engineering, biomedical coatings, tribology, corrosion, additive manufacturing, and materials characterization. And with the mentorship and active supervision of Professor Harpreet Singh, I'm sure we must have learned a lot of other things which are not listed here, but we very much on that note look forward to welcome Avnish to this ECR day, or ECR dedicated day of thermal spray week, and look forward to hear his thoughts on what he is doing in his PhD work. Avnish, welcome to the network, and hand over to you the podium.
Thank you, sir. Am I audible to you?
Yes, very much.
So can I share my screen now?
Please go ahead.
I think my screen is visible now.
Yeah, you can see the screen and start.
Okay, sir. Thank you very much, sir, for the introduction. So today I'll be talking about the cold spread coating for biomedical application, especially titanium-based composite coatings. So
Avnish, maybe you can speak a bit louder and hide your Zoom option button. So if you press hide on the bottom.
My voice is not clear. Are you saying that?
Your voice is slightly lower. If you can speak a bit louder. And
okay, sir. I'll try to speak a little louder. So is it okay now?
The sharing icon is appearing. Can you press hide there and the bottom?
Okay. Yeah, sure.
Yeah, that's it. Please go ahead.
Is it okay now?
Yeah, perfect.
Okay, sir. So today I'll be talking about the coatings which is developed using cold spray technology, especially biomedical based coatings. So this is the outline that I'm going to follow through my presentation, starting from the implant market, and then I'll end with the some performance characteristics of the already deposited titanium based coatings in our laboratory using cold spray facility. So starting from orthopedic implant market, so in December 2020, Fortune Business published a report and claimed that the business of the implants has reached to 20 billion US dollar in 2020. And they have projected that this is going to become a 26 billion US dollar in 2027. So these are some manufacturing industries which are contributing to this market for the manufacturing of these implants, especially Exatec, Johnson & Johnson, Zimmer Biomet, Stryker, Smith & Nephew, Conformis, and some other also is there, right? So then what is the need for implants? For example, I'll talk about the hip implant. So this is a typical image of a normal hip and a arthritic hip. So here you can see because of the arthritis, this hip completely got damaged. So arthritis is basically a disease where our immune system attacks the joint and rupture the cartilage in between the bones. Basically, cartilage is a tissue which helps to support the load carried by these bones, and it also helps to provide lubrication at the contacting surfaces. So based on the different type of attacks, arthritis has categorized in more than 100 types of arthritis. So osteoarthritis and rheumatoid arthritis are the most common arthritic disease, right? So what are the major solution to this type of problem? Basically, there are two solutions. One is steroid injection therapy, and the another one is the implant therapy. So in steroid injection therapy, doctors inject the steroids into the joints in order to recover the cartilage function or the lubrication of the cartilage, you can say. But the problem with this injection is that their life is very short, maybe around 3 to 4 months maximum, and this injection doesn't work for every other patients. So also this injection therapy is very painful. So on the other hand, we have implantation surgeries. So these, for example, for hip implant, the cost of one implant surgery is around 3,000 US dollar, while for the cost for one steroid injection therapy is around 400-500 USD. So the life of these implants is around 10 to 15 years. And the manufacturing of these implants is basically a two-step process. In first step, they prepare the base part of the implants using some advanced manufacturing techniques like additive manufacturing or some maybe casting process. So for that, usually people have used stainless steel, cobalt, chromium, titanium, and its like some polymers also like ultra high molecular weight polyethylene, highly cross-linked polyethylene. Then to further enhance the properties of the surface of these implants, surface modification techniques has been used. So in surface modification techniques, they have tried some machining of these implants in order to get better tribological properties. Or in some cases, they have tried to improve the surface roughness in order to get better biological properties. So for that, they have used grit blasting. And also people have used coatings to get better biological, mechanical or chemical properties. So for coatings, people have tried different materials, including titanium based alloys, hydroxyapatite, alumina, zirconia, and many more. And the technologies they have explored is include physical vapor deposition, chemical vapor deposition, salt gel deposition, and thermal spraying also. Thermal spray is also accepted as a uh, biomedical coating technique by US Food and Drug Administration. And in thermal spray, as we know, basically it contains three parts. So one is the material that we want to deposit. Another is a heat source, which required to melt this deposited particle, melt or semi-melt. And then there is a carrier gas, which propel this molten or semi-molten particle onto the substrate in order to form coatings. Based on these principle, number of coating technologies has been put forward, including flame spray, plasma spray, high velocity oxy fuel, high velocity air fuel, detonation gun. And using these thermal spray technologies, various materials have been explored for biomedical coatings, in which titanium and hydroxyapatite are the most popular one. So titanium is because it has superior corrosion resistance property. Other than that, it is very good in strength to weight ratio. Also, it is biocompatible. But the problem with titanium is that it is bioinert, which means body neither accept it as its integral part nor rejects it. So on the other hand, if you see hydroxyapatite is a mineral which is mimics the bone characteristics. So it is a calcium phosphate compound. It is very much biocompatible, but it is also bioactive in nature, which means that it helps in bonding between the bone and the implant surface. It also helps in growth of the cells onto these implant surfaces. But the problem with this material is its poor mechanical property. So in view of this, Professor Christopher has already discussed in his talk that they have developed some coatings of calcium silicate compounds, which is bagdadite, using plasma spray, and they have also prepared some hydroxyapatite based coating, and then they compared both coatings in terms of its mechanical performance and biological performance. So these numbers are nothing but some general features of plasma sprayed coatings. So number one is basically showing that the micro cracks developed in the coatings because of the, I mean, after remelting, they got cooled down, and because of that, some stress is generated into the coating, and then these cracks develop. Then number two is showing that there are some micropores also. Then some unmelted particle is also there, like that. Then he discussed in his talk that the micro hardness value of these coatings was far better than the hydroxyapatite coating, which we can see here. For bagdadite, it was around 325 HV, and for hydroxyapatite, it was around 118 HV. Similarly, for elastic modulus also, bagdadite was having 103 gigapascal, and around for hydroxyapatite, it was around 66 gigapascal. So from here, we can say, yes, the mechanical properties of the bagdadite was far better than the hydroxyapatite coatings. Similarly, they have also conducted some biological testing. So they seeded osteoblastic MG63 cell culture over these surfaces and found that the bagdadite was able to promote the proliferation of the osteoblastic cells in that environment. So basically, this bagdadite has shown better biological bioactivity or biological performance when comparing with the hydroxyapatite surfaces or titanium surfaces. Then the main problem with these thermal spread coating is the high temperature. These high temperature sometimes leads to change in phase of these coatings. So to see that, we have gone through their XRD results, and we found that before spraying, before and after spraying, there was some change in phase in both the coatings, in hydroxyapatite also and in bagdadite also. So they reported that the crystallinity of these coatings has decreased after spraying. So before spray, the bagdadite was having 55% of crystallinity, and after coating, it was around 21%. Similarly, for hydroxyapatite, it was 78%, and then after coating, it was around 64%. And they gave the same reason, high temperature, which was involved in plasma spraying. So this phase change problem can be avoided using cold spray facility, because cold spray is basically a solid state deposition technology where powder particles, micron size powder particle, propelled with the supersonic velocity and strikes the substrate to form bonding, mechanical bonding or metallurgical bonding. So to attain that supersonic velocity, convergent divergent type of nozzle can be used. So this is the cold spray setup we have at IIT Ropar, and this setup can spray up to 50 bar of gas pressure and 1000 degree of gas temperature. So while spraying these powders, I try to capture this video, which you can see. So this is the titanium we sprayed on SS316 cell substrate, and you can see the flashing jet uh, you can observe. That is because the titanium is pyrophoric in nature. So yeah, after that, as the particle strike onto the substrate, it form bonding, and that bonding can be described using several bonding mechanisms. So the first one is oxide layer breakup. So when this particle strike with very high velocity onto the substrate, it breaks the oxide layer if there is any on the substrate and form a new surface for the bonding. Similarly, there is another bonding mechanism which is adiabatic shear instability, which says that for particle to adhere, there is a threshold value of velocity which it needs to reach. And at that velocity, basically what happens when it strikes, particle deforms severely, along with the sudden rise in temperature is observed at that particular velocity, and also particle loses its flow strength. So when these three things happen together, then this condition is known as adiabatic shear instability. So because of the adiabatic shear instability, particle flows from the contact, and one jet-like features occur, which is given the reason behind the bonding of the particle onto the substrate. And these simulations has carried out by assuming that both the substrate and the particle both are same material. Then if the material is different, I mean the particle is having different material and the substrate is having different material, then in some cases it was observed that this sudden rise temperature reaches above melting point, and then some localized melting occur at the interface, which helps in further bonding. So then for mechanical interlocking, researchers says that this jetting sometimes lock with the other particles jet or the substrate jet, which form mechanical interlocking, and it promotes the adhesion or cohesion of the particles. Then there is another theory, hydrodynamic plasticity, which says that this for jetting, this thermal softening is not necessary. So Hassani Gangraj group says that for good bonding, the thermal softening is not necessary. I mean, for jetting, thermal softening is not necessary. So they simulated single particle interaction using thermal softening effect and without thermal softening effect. And they found that without thermal softening, also jetting is occurring. Then what are the reasons behind this this jetting? So for that, they are saying that when the particle strikes with very high velocity, then at the contact, high pressure shock wave generates. These high pressure shock waves try to detach the particle from the substrate and to take the jet out. So to confirm that, what they did one simulation of single particle without using this thermal softening effect, and they said that on impact, a highly compressed state of matter is formed at the contact zone, which expands as the impact develops, and the particle flattens to create more interfacial area. So the velocity at which this particle flattens, they named it as contact edge velocity, and the velocity of the shock wave pressures they named that is Vs, shock wave velocity. So this is that at a particular time when initially that contact edge velocity is very high, and slowly this contact edge velocity decreases with time. So there is a point where the contact edge velocity become lesser than the shock wave velocity. And when it becomes lesser than the shock wave velocity, these pressure waves start releasing from the edge of the particle towards the free surface. And further, this release of these pressure wave caused the formation of jets. So you can see the same after 2.5 nanosecond, this jet formation is there. So in both the theories, they says that the jetting is necessary for bonding, but they are contradicting on a point that thermal softening is not necessary for the jetting. Then till now we have talked about the metallic materials bonding. Now what about the ceramic particles? So to see whether ceramic particle retains onto the substrate surface, this Rohan Chakrabarti with his group did some simulation on different substrate conditions from softer to harder, and he saw that for on harder substrate the retention was minimum, but on softer surface the retention was there. As we all know, when ceramic particle strikes onto the strikes with very high velocity, so either it got rupture, fracture in fragmentation, or it deformed very minutely. So the retention of these ceramic particle on the softer surface is they connected with the crater depth. More the crater depth, better will be the retention. So however, they said that if the jetting occurs at the interface, then the retention will not be there. This jetting will take the fragmented particle out from the surface. Then they also saw the effect of grain size of the ceramic particle onto the retention. So for that, they have taken a titanium oxide particle and they impacted the titanium oxide particle onto the copper substrate with different grain size. And they have seen that a higher grain size particle is retaining more after impact. And the reason they gave is that the dissipation of kinetic energy through fracture is lower in this larger grain size case. Then what is the role of surface roughness in bonding? So this is also very contradictory topic. Lots of researchers are saying that rough surfaces are good for bonding, and then there is other groups which are saying that polished surfaces are good for bonding in cold spray. Even some of the groups are giving the roughness number also, that how much roughness we need for the good bonding, as they are saying that rougher surface helps in interfacial mixing. So however, they are also saying that further we need to investigate whether this much coating thickness, this much roughness is okay or not. So some of the researchers are also saying that grid blasting is helping in bonding, because grid blasting helps in breaking the oxide layers and promote the adhesion at the contact. Also, grid blasting creates rougher surfaces, so that also helps in interlocking. On the other hand, the researchers are saying that a polished surface provides uniform area for heat dissipation for particle to substrate, which further helps in thermal softening. And then for grid blasting, they are saying that grid blasting leads to surface work hardening, which reduces the deformation ability of the substrate, and further the bond, it affects the bonding in a adverse way. So from here, it was not clear that whether we should use rough surfaces for good bonding or we should use polished surface. So that's why we have started our work from here only, and we have prepared 3 different surface roughnesses. Uh, uh, as you can see here, so the substrate we have taken was SS316L substrate, and it was having different surface roughness. So AR stand for edge received substrate. So edge received means the average roughness value is around 5 micron, and for semi polished it was around 0.5 micron, and for mirror polished surface it was around 0.03 micron. So and then we impacted this titanium particles, we and so the single particle interaction from the top surface. And we have seen that in all the cases there was jetting, but the jetting was most significant in case of mirror polished surface. And then it was minimum in case of semi polished surface, and then there was some jetting on edge received surface as well. So, and as we have discussed above in the bonding mechanism, that the jetting is the main reason for the bonding. So to further see that what is happening at the interface, we did some cross-sectional SEM image analysis of cold sprayed titanium particle. There we have seen that in case of semi-polished, there was no bonding. However, in case of adhesive substrate surface, there was good bonding and the particle was able to deform. But in mirror polished substrate surface, if you see that the particle was able to deform completely and it adhered very well with the substrate. So to further see which one is better, we have analyzed the cross section of single layer cold sprayed coating. And then we have seen that in edge received case, there was some voids between the particle and the valleys of the surface, and these voids basically influence the bonding in a negative way. And then in the semi-polished case, we have seen that there was a thick crack or a gap between the coating and coating and substrate, which shows that there was no bonding. And then in mirror polished case, we have seen that there was no gap or crack at the interface. So from here, we realized that mirror polished surfaces are good. So the reason behind it was that in as received substrate surface, the peaks and valleys are higher and deeper. So these peaks and valleys restricted the deformation behavior of these particle. And in case of semi-polished substrate surface, the peaks and valleys were smaller in size, but they were large in number. So when this particle impacted with very high energy onto these peaks and valleys, all the energy of this particle is absorbed by these peaks and valleys, because of which this particle was not able to deform. And also the contact area was minimum in this case, because the contact of the particle was with the peaks and valleys, with the peaks. However, in this case, the contact area was maximum, and particle was able to deform completely and able to transfer the energy of the coming particle to the substrate. So which also influence the thermal softening effect, because it is uniformly transferring the heat energy to the substrate. Then after that, we have also done some scratch adhesion analysis, which supporting the same data, which is saying that mirror polished substrate surface is good, but because of the time limitation, I have not given the data here. Then after that, I realized that we have to, then after those results, we have realized that, okay, mirror polished surfaces are good for bonding. And then we sprayed these titanium and bagdadite particles using cold spray facility. So titanium, because to spray bagdadite and to deposit bagdadite is difficult, because bagdadite is ceramic in nature, and we have seen that previously in the bonding mechanism of ceramic particles. So for that, we need a metallic material, which is we use titanium, which is having good biocompatibility and good strength to weight ratio. So we mixed these powder particles in different ratios. So here, this is the coating designation we are going to use throughout. So 10 represent the 10 percentage of bagdadite, and 15 represents the 15 percentage of bagdadite. So in this ratio, we mix the powder particle mechanically and spread onto the SS316 cell state. So these are the etched cross-section images of the coating. And from here, we can see that there was significant amount of ceramic has retained into the coating. So for confirming the retention of the retention of the particle into the coating, we have taken some high resolution SAM images at different location, and then we mapped them using. Then we have used images software to see how much percentage of bagdite is retaining. We found that it was around 60 to 85% of the retention was there, and that depends also on the coating composition, right? Then the main thing was the phase change problem, which we were having in plasma spray coatings. So here we did some XRD analysis, and we have seen that there was no phase change in the coating after the spraying. Then with the increment in bag percentage, seen that porosity and surface roughness is increasing constantly. However, the coating thickness has decreased. So the reason for that can be that when the ceramic bagdadite particle strikes onto the titanium particle, or to the ceramic particle itself, or to the substrate, so either it got fracture, or it got very little deformation, plastic deformation. So this leads to some voids around the splat boundaries, and cause to the formation of porous coating. So that's why with the increment in bagdadite content, this porosity has also increased. And it is also expected that as the backlight content will increase, the interaction of ceramic particle will increase, which will also influence the coating thickness. And these are some research groups which have reported the same type of results. Then we have done some biocompatibility analysis. So for that, we put our already deposited coatings into a cell culture, osteoblastic cell culture, for 24 hours, and monitored the cell viability. Cell viability is nothing but the live cells. So the threshold value was 70%, and we have able to achieve, more than 70% of cell viability, which says that all the coatings were biocompatible. So after that, we did some corrosion analysis in simulated body fluid environment, that is in Ringer solution and we have seen that all the coatings were successful to protect the substrate from corrosion. And as the bag content increased, the coating has shifted towards the noble direction. Means the stability of the coating has increased into that environment. So to see why all the to see how this coating is performing well, we did some post corrosion analysis also. So here you can see this is the substrate before and after corrosion. So before corrosion, this was the substrate. After corrosion, you can see how it gets deteriorated. Even the one layer, top layer of the substrate is got peeled off. So then we also did some SAM and EDS analysis of the corroded coatings to see that what is happening onto the surface. And for that, we have found that in all the cases, oxygen content has increased immensely. So we also mapped this titanium 25% coating, And we found that yeah, there was some sodium also, calcium, oxygen, silicon, titanium was we were able to detect. Then to confirm whether there was some formation of these oxide layers was there which protected the substrate surface. So we did some XRD analysis, and in the XRD we found that there was some calcium oxide layer was there, then silicon oxide was there, then titanium oxide was there, which helped to protect the substrate from corrosion. Actually, they worked as a barrier to electrolyte to penetrate through the coatings. Then after that, we did some similar performance analysis using pin on disk test. And then before doing that, we did some micro hardness analysis on the cross section of these coatings. So from the cross-section micro hardness analysis, we realized that as the bag content increases, the micro hardness value also increases, but there is a threshold value. After 15%, it decreases continuously. It is because maybe as bacteroid content increase in the feedstock, so it also influences the bonding between the particle, interparticle, like between bacteroid and titanium, because it will interact with the titanium particle also, and it will affect the impact velocity of those particles. So further the deposition will got affected. So the cohesion strength of the coating will also got affected. So yeah, that can be the reason for the decrease of this micro hardness value. Then we monitored while doing sliding wear test, we monitored the wear volume, and using this equation we have calculated the wear rate. So these tests we done in dry condition and simulated body fluid condition. In dry condition, we have seen that only one coating was able to protect the substrate, that is titanium 15% bag coating. And however, if you see the hardness of this 10% coating is higher than the substrate. And as Archer's wear law says that the wear rate is inversely proportional to the hardness of the coating substrate, coating surface. However, still the substrate was having better wear resistance than this. So the reason for this can be that the substrate we used was mirror polished. So the initial wear in that case was minimum. But in if you see in this coating, these coatings were as spread coatings. So we were having some peaks and valleys. Those peaks were hard enough, but because of the high concentration stresses high concentration stresses, severe plastic deformation of those peaks occur, and initial wear caused the high wear rate. Then in simulated body fluid condition, this only two coatings were able to protect the substrate, that is titanium 10% bag and 15% bag. And the reason can be explained with the hardness. More the hardness, better will be the wear resistance. Similarly, for coefficient of friction, usually coefficient of friction is independent of all these things, but there are some literature which says that coefficient of friction depend on contact area. So here, if you see the maximum coefficient of friction is in 25% bag and the minimum is in 15% bag. So it is because the bonding was relatively loose in 25% bag. As you can see, the hardness value is also very less, which indirectly tells about the bonding also. So because of the severe plastic deformation, the wear debris are very high in this case, which we will see in the post wear analysis. So these are the coatings after post wear analysis. So this is under dry condition and this is under wet condition. In all the coatings, we have observed some signatures of micro cracks, pittings, micro cuttings, and wear debris also. So these wear debris are smaller in size than the particle we used earlier for the spraying. And these wear debris may have taken the part in abrasion also. So that can be a third body type of abrasion, which has influenced the wear rate also. So these features are common in every cases. And so yeah, those are the, I think, the reason for the high wear rate in these coatings. Then we try to see whether there was some transfer of material from the coating surface to the counter surface, and for that we have done some SAM and ADS analysis of the counter surface, that was alumina. So for alumina, we have found that in every case there was some titanium there, which is green color in every case. So which means that material has transferred from the coating surface to the counter surface. And the reason for that can be when the one surface is rubbing the other surface, then there will be high temperature rise at the contact. and that high temperature rise will cause the development of weld junction between the coating and to the substrate. So this will lead to the transfer of material from one surface, that is softer surface or coating surface, to the counter surface, that is alumina surface. So yeah, so from this we have concluded that we were successfully able to deposit titanium based composite coating on SS316L substrate, and there was a significant amount of baghdadite that retained into the coating. So the coating protected SS316L substrate from corrosion because of the formation of these calcium oxide, silicon oxide, and titanium oxide protective layers. And then we have seen that among all the investigated coatings, 15% of baghdadite composite coatings is found to be the most successful in enhancing the wear resistance. It is because of the superior wear resistance of this, superior hardness of this 15% bag composite coating. And the wear mechanism we found was micro cutting, micro cracks, pitting, delamination, which are the features of abrasion. And then we have found some mass transfer also, which is also the feature of adhesion in the alumina counter surface. So after that, we have also done some post laser treatment of the coatings, which we have not shown here, and those results are under consideration in one journal. So yeah, thank you for your patience. Now I think I'm open for questions. And in the end, I want to thank Dr. Saurabh Goyal and Dr. Pamela for giving me the opportunity to present my work on this DSM network platform. Thank you very much.
Thank you, Avnish. You're very welcome. But you have already done a lot of things. Actually, I was very impressed.
Thank you very much, sir.
I noted that somebody made a question, so maybe let me
Yes.
ask if there is a question.
Thank you, Avnish. Excellent presentation on, the cold spray. So far it has been only on, pure metals, ductile elements, and this is an eye opener to sort of mix ductile with a brittle material to spray. I think it's a great initiative. So
Thank
my
you,
question was, if you sprayed it on 316, which is a hard substrate, right?
yes, sir.
And you were able to get good adhesion with micro polishing, mirror finish kind of surface, right?
Yes, sir. Yes, sir.
So in the real world, if you were to do it, there will be obviously some challenges, right? If we have to do it on a implant, we obviously cannot get a mirror finish, but what do you think, can be done there in a commercial world? How can we improve the adhesion of this material to commercialize it?
Yes, sir. So, sir, initially, as I started my talk from the grit blasting thing, so initially people were saying that grit blasting is good for the adhesion. And then we have seen that, okay, mirror polish also helps in better bonding. But yeah, there are some cases where we have seen that people are saying that because whatever surface we are receiving in industry or like for implants also, that will also give good adhesion, but relatively mirror polish substrate surface is giving better adhesion. So yeah, further, I mean, this
So
topic needs to be
so the corrosion studies on an as received surface, could be a bit different than what you are showing. Maybe that's a worth study, I think, in future to compare it.
Yeah. In some cases, actually, people have shown that the surface preparation actually affect these properties also, like corrosion performance, and also some properties like elastic modulus, micro hardness, or maybe in some cases thermal conductivity also. People have reported that it get influenced because of the surface preparation.
Yeah.
So yeah, that can be I mean, an interesting thing to look for.
Yeah.
Sure,
I think very impressive work. Congratulations.
Thank you very much, sir.
Okay, thanks a lot, Vish. So Avnish, I have a few questions, not technical type.
Yes, sir, sure.
But in the interest of perhaps this network, So my
Yes, sir,
first
sure.
question is that I see that you were present in some of the other talks also on
Yes,
the
sir, sir.
same days. So as
Yes.
an ECR, how do you see this type of event has benefited you or has groomed with this kind of exposure to talks from other people who are experts? How do you see
Yeah.
this has helped you and your career?
So, sir, first of all, I would like to say thanks to DSM Network also, because they have given us the opportunity to understand what is going on in thermal spray area nowadays. And also, we have learned a lot from the experts, like what type of work they have done in the area of thermal spray. Like I am now aware of biomedical things and the things that my supervisor is working on nowadays. But when you see over around the globe, that how people are working in thermal spray, how they try to improve the facilities, and how they are trying to uh, predict the different properties of of the coatings, like using AI or simulations. That is quite interesting to see. So yeah, it helped me immensely to know about things which I never knew earlier. So yeah, it was great help.
Okay, and in your own perception per se, or in your own judgment,
Yes.
because let's say you are coming from IIT Roper based in India, which area in thermal spray manufacturing did you see that your institution or India needs more push or momentum?
So right now, I think, yeah, this biomedical thing is very, important and very interesting. Very few people are working in my IIT. I think nobody is working in these things. Harpreet sir is working in thermal spray, but not exactly for the manufacturing of implants. So like we have explored the coatings, but not exactly the how can we prepare the full-fledged implant. So these things, I think, we should look for. Other than that, like hot corrosion, this is sir's expertise in uh, hot corrosion and cyclic oxidation like things. So that is also, I mean, they have published some patents also on that thing. So yeah, in that way we can improve the, performance of different components in industries, and it can help economically also.
Okay. And in your personal ambition, do you have aspirations to join academia or to go to industry?
No, sir. I wanted to do some research things. From the academia point of view, and then I'll see what opportunity I will have,
Okay.
because I want to explore more in research things, maybe in
Yeah.
industry also. Yeah.
Great. All right. Thanks a lot, Abneesh, for that
Thank,
valuable time and presentation that you prepared.
thank you very much, sir.
So thanks again.
Thank you. Thank you very much, sir, for
Okay.
giving me the opportunity.
All right. So let us then now welcome our next speaker. So our next speaker would be Vish, working with me actually at LSPU. And as such, introduction wise, I mean, he's a expert, I would say, in thermal spray readily. I mean, he's although hailing as an ECR for this event, and he is classed as an ECR, being new to the academic community. But he has actually been working in an industry for well over 15 years, and in industry, not an ordinary industry, but GE, who are one of the prime consumers of thermal spray manufacturing. So he has perhaps taken a very positive move in his career, and very bold step to transition from an industrial journey back to academic journey. So currently he has joined as a postdoctoral researcher working on a EPSRC exploratory manufacturing project, which is termed as Coat-In, to develop functional coatings which will be capable of in situ monitoring of functional life of the coatings. So very ambitious project in itself, which is an outcome, in fact, of the DSM network as such itself. So he's trying to currently look into closed loop robotic control of thermal spray process. And by his arrival to LSPU, working with me, he brought with him extensive industrial experience of GE, as I said, but also there are a lot of supply chains associated with GE, and he has a multitude of experiences working in different parts of the world, including Singapore, US, Dubai, India, and so on. So in those areas of thermal spray, he has spent a significant portion of his life developing coating parameters for aviation and power generation components, like to the robot programming knowledge of free-form profiles, mathematically complex, to be coated with thermal spray. He did his PhD prior to coming to LSPU, of course, at Purdue University in the area of plasma processing for detection of nanostructures, wherein sprayability of nanoparticles using thermal spray was extensively studied and explored by him. He aspires to excel in academia, of course, with his arrival now, and would like to basically bring the contributions from industry side to contribute further to achieve the global goal of sustainability in materials and manufacturing through approaches like digitalization and to develop sustainable alternative materials. Now, today he is going to focus, because he's one of those candidates coming from industry, and he's acutely aware right now of academia. So he has taken a very challenging topic of trying to put together his thoughts on how he see the bridge that is necessary for academia industry to work together under one single ecosystem, which is where EPSRC DSM NetworkPlus positions itself in that ecosystem, is to be an interface between that industrial academic landscape. And so this talk as an ECR is a very bold step, very timely, and we very much look forward to hear Vish. So Vish, without any further ado, I'd like to welcome and give you the floor for sharing your thoughts in this.
Thank you very much, Dr. Saurabh. It's been a pleasure working with you for the last 3 months. And thank you, DSM Network, for this opportunity. After, this is the 4th day, and all the last 3 days has been an eye-opener for me in terms of listening to the experts from Concordia and Stony Brook in the west, all the way to IIT Roper in the Indian subcontinent. A lot of new things to learn from the academic world, and a lot of things to contribute in this field. So that I would like to share my, sorry, I hope you're able to listen and look at my screen as well. So my topic today is on bridging the industry academia gaps in thermal spray. So taking a leaf out of Professor Sanjay Sampath's invention innovation theme, if we started inventing, which is kind of like a passion and a hobby, and if we can take a step forward and do an innovation which is useful to the community, it will be a great satisfaction to us in terms of career and profession that we do. So with that thought, I would like to get into the what we can do for industry from academia. My name is Vish Venki. I am a postdoctoral research associate working with Professor Saurabh Goel in digital and sustainable surface manufacturing at London South Bank University. I would like to just touch upon a few of my background and experience working with the industry. I did my bachelor's and master's in metallurgy and material science from India, and went on to pursue my PhD in the US in the area of surface engineering, wherein I focused on plasma spray, HPF, monitoring and diagnostics. And primarily my thesis was on how to retain the nanostructured coatings in the high temperature regime, whether it is plasma or ceramics, carbides, cermets. Is it possible to retain and do a industrial scale up to coat such nanostructures. So I would like to show you some pictures, and in the later part of this presentation on my PhD work. And during the course of my PhD, I also had an opportunity to work with Siemens, Professor Sanjay Sampath's alumni, based out of Siemens. They gave me an internship, and I worked with them on a variety of thermal spray equipment. So with that background, I got a job opportunity as a robot programmer in General Electric in India. I worked for about 8 years before, after I completed my PhD, wherein I had an opportunity to perform robot programming on complex geometries like airfoils and nozzles, thermal spray, primarily plasma spray, HVOF. And I also set up a lot of environmental testing facilities for GE, like oxidation testing, burner rigs, furnace testing. Also did a lot of thermal cycling studies on the niche coatings for high yttria stabilized zirconia compositions, as well as what we call as low conductivity coatings. We ran several R&D programs for oxidation coatings, like high melting point bond coats for thermal barrier coatings. So primarily I worked on the new make side of GE to develop coatings. Then I had an opportunity to move on to the repair side. From 2016, I moved to the Middle East, looking at coatings repair, diffusion coatings, non-standard offerings for Middle East customers. Robotic programming was still part of my job on the repairs portion of it, and I developed a lot of coatings for the Middle East customers, power generation for the 6B and 9E turbine frames. And I also, shortly after then, I moved to Southeast Asia, primarily based out of Singapore, for GE, working for aeroderivative engines, coatings like for LM2500, land and marine, we call it. There is plenty of coatings that goes into that product. That engine is used primarily for propelling the ship, as well as small scale land turbines. Most of the coatings that you will see coming out of Southeast Asia is probably the parameters were developed by me for the last 3 years. It has been a big privilege for me to develop and deploy coatings for manufacturing such high technology applications. So with that background and experience, I would like to talk about today about the how to bridge the gap between academia and industry per se. So let's look at this slide. Looking at this slide, just sort of made a Venn diagram of what the academic offers currently, and what the industry needs. And what do we have in common between the academia and industry, and how the OEM is actually supporting this industry. If you look at on the left side of the slide, we got we develop a lot of new chemistries in academia. We talk about a lot of novel processes, novel chemistries. We do a lot of science, and oftentimes, it will have a single parameter to show in the form of a publication or a patent. We normally do microstructural characterization and some mechanical characterization. We have an idea and a thought, and we do have physical sciences background skills that work on academia, materials and mechanical engineers who take this forward. and show an idea or a concept in the form of a publication or a patent. We also do a lot of simulation modeling to predict what's going on in the coatings world and how can we improve things, which is sort of what the industry needs, right? We do have novel, they do want novel chemistries, novel process. And the academic offers the talent and data that's on mostly on coating science. But let's look at the right side, what the industry needs, right? They have a focus to reduce the cost, so they want productive chemistries. They need thermal spray parameters that are repeatable, meaning that can we deploy it for days together and still get the same data? Do we have the choice of equipment that is perfect for this coding type or the application? They also need support with waste disposal, how to recycle. Is it possible to recycle and avoid the waste that is generated in thermal spray? How can we improve the deposition efficiency or make the guns a bit more robust and coat much more thickness in a shorter period of time? The most important thing is they need an interdisciplinary skills, like they will probably need electronics, electrical engineering, mechatronics with background, material science obviously, and a lot of physical sciences to work as a team to get the product out. They also rely on a lot of external supply chain for thermal spray applications. Oftentimes, there is not one single location where they can do a lot of coatings. So they need a good supply chain. These days there's a lot of talk about how can we use an operator just to push the button, get the thermal spray coating done. A lot of robotic programming can have this switch on the power coating gun, turn the powder on, turn off the powder, turn off the gun, get the part out. Can we fully automate that process? Industries want that kind of a solution. Most often, they talk about, how can we, not do any section cross-section analysis of the coating. No need of microstructure. Can we just do any non-contact characterization? Reduces the cost, gets the part out to the customer much faster. And obviously they much more than that, they need a talent, manpower to sustain thermal spray in the long run. So it's a special process. Not everyone can do it. And academia plays a very important role in sending that right talent to industries. If you look at the right side, OEM supports a lot of these industries that do thermal spray, but kind of a touch and go. Like they will give the equipment, they will provide the powders and the necessary infrastructure, but oftentimes, they kind of rely on this talent that academia sends to the industry to sort of sustain that thermal spray advantage. Moving on to sustainability. So what I'm going to do is I will touch upon a few topics that industry needs and how academia can support that. So if you look at sustainable thermal spray, it could be the first thing we look at, spraying a powder, spraying a coating is, OEM will give us a parameter. Is it relevant to my equipment? You might have HVOF system, but the OEM powder is actually made for a plasma spray. So things of that nature. Do we have the gases that the OEM is suggesting? And if I take that OEM parameter and spray multiple times, am I going to get a repeatable microstructure? Am I using the right gun to not waste a lot of powder? Am I putting a lot of powder on the floor? Can I improve the deposition efficiency? Can I spray faster for the same thickness? Can I spray faster and get the parts out? Is there a better gun to save cost and time? Can I use a larger bore plasma spray instead of a narrow bore? And what is the long-term maintenance cost of the equipment? Am I going to keep on changing my nozzle and hardware, or change my chiller system or the power supply to sustain that kind of customer volume? So when we develop these parameters, we have to ensure like a lot of these things in mind, to give them a parameter that is long lasting, so that they don't have to do a lot of maintenance, change a lot of equipment in the long run. So I think they don't have time. They probably can rely on such academic consultants to sort of give them a foolproof solution to keep this. And this by itself is a lot of savings to the industries. As we speak, the industries are spraying coatings with less efficiency. So there is a lot of scope to improve that. This slide is about, if you look at plasma spray itself, how we can, there are a lot of guns in the market. And if we choose, a low power gun for a high throughput process, we are going to end up having a lot of porosity and unmelts in the microstructure. So, choosing the right gun for the right process, wherein, the materials property, like physical properties, density, melting point, on the one hand, and the throughput of the process in the other hand, is going to decide what type of guns we choose to get the right microstructure. So Plasjet, the recently MedTech Axial 3, they're going to have a great advantage over the other Medco guns in terms of getting the high throughput coatings. Triplex Pro also has a lot of advantage in terms of putting a thick coating in a very short span of time. So speaking about non-contact characterizations, can we do away with metallography? It takes a lot of time, and it uses some chemicals, acids, etching. Can we do and mounts are made out of epoxies? If we can do away with that and use a non-contact, much similar to like what we do for eddy current analysis of top coat TVCs. Is it possible to use the electrons, photons, and phonons to detect the coating defects? A lot of them are actually getting industrialized. Like if we can use millivolts and microvolts to know if there is a coating or not, it's by itself, we can avoid a lot of metallography work. Can acoustics technologies, we have some initiative going on at LSBU to determine the health of the coating or the health of the equipment using just with the acoustics. How to check the porosity or cracking or delam in the coating using acoustic waves. Do we have can we measure the thickness of metallic coatings with the eddy current equivalent? This is a big challenge in industries currently, where they cannot measure the bond coat thickness without sectioning the samples. So we can contribute on that a lot. And also A grid blasting interfacial contamination is a big challenge, and industries are looking for a non-contact solution for that. More often, the cutting edge talk that is going on in industry is, if can we use electromagnetic waves, not just the light on optical range, but the electromagnetic waves to determine the coating thickness as the coating is depositing live. Right now, there are some white light, blue light technologies available after the part is coated and cooled, but not to an extent where, when it is currently coated, do we have some sort of that technology to take it forward? So thermal spray has a lot of variables, right? It's going to be confusing for a novice to look at so many parameters and see which ones to change and which one is not to change. So if you have to end up automating this process or semi-automation, what are the things we need to look at? Primarily, we have gas flows, spray distance, robot speed. Can we turn on these knobs favorably to get a coating, right? So what we do now is we do a accurate spray window wherein we study the temperature, velocity, and the intensity of the plume, and say, hey, everything is within the range, and we get the microstructure out. The next feature is going to be, and it's imperative that the industry is going to demand that, and we have to move towards it. That technology is, we get these parameters using the in a measurement window, and change the gas flows and input parameters seamlessly, automatically using a robot. So there could be this process outputs that is shown on the bottom right of this picture on this slide, and if the robot can be fed with those parameters, the robot should be able to turn the knobs of gas flow and spray distance and robot speed by itself. This is a highly interdisciplinary approach wherein we need material science, electronics, electrical, and PLC background, Python, MATLAB experts to come together and do this. This is the future. I think it's going to disrupt the thermal spray world more than ever. And I think we should all be collectively working together in giving the solution. It's going to save a lot of cost and time to get there, and it's very highly efficient way of doing thermal spray coatings. So we have some work going on with the DSM network, University of Sheffield instrumentation team and LSPU are closely working together to get some sort of initiative going in this regard. Other thing is, we need to have offline robotic programmers who can support thermal spray in a much better way. Offline robotic programming is when you just do everything from your computer using CAD software and code these parts. So it's it takes this precious cell time, so you don't have to work with robots. You can work with just program it in your PC and put them back in the robotic controller, and it works. And that's how industries operate. I think we can give them a seamless solution. Not many thermal spray industries have that kind of technology, but I think academics should sort of collaborate together to get industries this kind of solution, which is going to be a lot more productive and a lot more quality and sustainability. So in the materials aspect, coatings revolve around this periodic table, right? We just, if we look at this periodic table any time of the day, and there are a handful of elements that we coat, mixing it in a certain proportion, and that's what we do. Tungsten carbide, cobalt, nickel, conich and nichrallies, yttrium stabilized zirconias, and we're trying to tap this lanthanides series elements. A lot of work is going on to substitute for yttrium. Please note that this lanthanides are available in one country in the world, and we don't know how the supply chain is going to be. In terms of, are we going to keep on relying on that one country to, supply thermal spray ingredients to the whole world? We need to look at alternatives, right? How we can. Yttrium itself is a critical raw material, and so are many, like, for example, chromium is hazardous. How can we move away from chromium? Can we put less nickel, less cobalt? Things of the, recycling is the key to avoid tapping this lanthanide series is a must. And these are the challenges materials wise. And now industries are talking about hydrogen turbines, high efficiency turbines, right? They also have challenges to design turbines with high efficiency. And unfortunately, without these high, rare earth elements, it's going to be difficult to sustain that design initiative taken by the corporations to have a sea change in the turbine technology. So how do we sort of catch up with that technology by we still have to use this rare earth, but in a sustainable way. So there's a lot of work to be done in terms of getting the chemistries right in a sustainable way. So this is slide is about how we can develop the chemistry and develop the parameters, test them to industrial standards, provide a seamless solution to industries. If we look at a circular economy, we just have to tighten the amount of powders we put it on the floor. If we reuse the powder, can we reuse the yttrium stabilized zirconia that goes on as a waste? Most of them goes to the landfill. So we need to be thinking about reusing them. If 2 billion kilograms of powder, 2 million kilograms of powder is going to be sprayed of YSZ powder, 1 million kg is going to go on the floor, on the landfill. So a lot of things can be done to recycle and reuse that powder with the help of academics. I think we can do a lot of initiative on that front. Looking at some of the opportunities that I just jotted down a few of them here. Can we look at manufacturability, improving the manufacturability of perovskite cells, calcium titanate, using thermal spray, or solution picker plasma spray? That would be a great approach to. It's a niche area. I think a lot of renewable industries would be more excited to get that kind of technology. Erosion in wind turbine blades is still a problem. I think we have wind turbine blades in GE, especially. If you look at some of the high rain monsoon areas, the rain droplets sizes are so low that the leading edge of the wind turbine gets eroded, and sometimes we have to scrap the whole blade, which is highly environmentally hazardous way of disposing those blades. So if we can use thermal spray to do erosion protection of those leading edges, it will be a great support. Another option is, I was thinking of, with there are so many stainless steels, just to keep them from corrosion or erosion, hardness, high hardness, tool steel application. So if we can induct more carbon steels just by doing thermal spray substitute, I think we can save a lot of energy and save a lot of nickel and chromium. Identifying yttrium alternatives, like I said, every aircraft industry and power generation industry is going towards using yttrium in a much more volume, because they want to hit the high efficiency turbine goal. So yttrium is much more sought after material than ever. But if there is an alternative to yttrium, I think we should do it now, and this is the time to do it. A lot of processes are solo right now, like HVAF, plasma, they are done in solo. If we can combine a cold spray with an additive process in one, to shrink the shop floor layout, do a tool change using a robot and perform one or two processes or three processes in one layout, I think that will save a lot of manpower and process inputs. More importantly, we are moving towards CMC composite turbines, right? Silicon carbide is going to be the future. If we can spray silicon carbide with a cold spray process or a SPPS process, I think we are going to have a lot of opportunities, especially environmental barrier coatings, high throughput. Professor Joshi was talking about high throughput solution precursor spray process yesterday, and it's a very good opportunity for us to tap that for silicon carbides in future. Most of the gas turbines in the future is going to be CMCs, so we should be prepared for that. A lot of wind turbines, the towers and hubs and nacelles, a lot of this VOC paints. European Union has got a lot of, the restriction towards using these VOCs, but not many countries have that. So we're still using a lot of volatile organic compounds in those paints. Thermal spray zinc and thermal spray aluminum are the future to replace this, high VOC paints. So with some work can go in that regards. Looking at the current status, right? The big corporations have this, sort of the ecosystem where they have this PhDs and materials team and interdisciplinary engineers working on parameter development, robotic programming. There are a lot of industries that they don't have this bandwidth. So they spend a lot of time and money to develop parameters. And I think academics can definitely help to sort of, using knowledge transfer agreements, we could help them with a highly efficient process in one shot. So they keep going and they can reduce a lot of plant and equipment costs. If we could take down on the ceramic powder waste, metallic powder waste is still a good recycling business now, but the ceramic powder waste is mind-boggling. And I think we as academics should actually jump into it and look at a lot of this recycling efforts to be sustainable, especially OSG is a big landfill waste. And also we should be able to go to the extent of consulting to industries that needs the right equipment and process to upfront, so that they don't have to keep changing their layout and equipment, which are more time consuming, and they have to disrupt the whole production line to do this. So it would be worth putting the right things in the right place in the beginning. We could have a continued discussions with OEMs to recycle and reuse the powders. It's going to be more than important that the supply chain is going to be disrupted with this geopolitical situations of having to rely on a single country to on the lanthanide rare earth elements. So wheel feeders, and I'm a big fan of wheel feeders. They're quite good. It puts in a lot of powder very consistently, and fluidized bed feeders obviously takes a lot of maintenance time. That's my opinion, but I'm still sure that a lot of industries use these feeders, but there's a lot of optimization that could be done just by changing the feeder from fluidized bed to wheel feeders. I think we should have a Wikipedia of thermal spray by itself, in the sense that parameters should be open to open domain, and a lot of industries can be benefited. It's going to be a big win in terms of helping the small scale industries to come up to speed, and do thermal spray in a more sustainable way. And I feel that academics have a big role to play in terms of sending the right talent to the industries. If we could have a thermal spray degree or a course, for example, with all the things being taught, robotics, CAD programming, materials engineering, and electronics, PLC programming, I think that by itself, so if we can send one guy to the industry with all these skills, we are doing a big service in terms of wastage and right talent and productivity. I think we should all work towards that, get in a big way. This is a cartoon of, and I think if you could get a chance, and please go through that the recent article that we wrote on thermal spray role in combating climate change. In every industry, does a lot of emissions, but like Dr. Sampath said, it's very insignificant that when you compare it with other industries, or thermal spray emissions are very minuscule, but it adds. So I think we could take out as much hydrocarbons and acetylene and all those things out, and if we could put in a lot of hydrogen as a process fuel, argon, helium, I think it will contribute to the environment. And a lot of this epoxy products gets wasted when we do thermal spray, like masking is a big waste that gets generated, and it goes to the landfill. So if we could have sustainable organic masking technologies, I think it will help to reduce the waste. So here are my few thoughts, some more ideas on how we can do collaboration. A lot of polyesters are used in upgradables, like the shrouds of the turbine engines, actually the tip of the blade and the casing. So they basically, polyesters are used to increase the porosity in the TBCs to get that upgradable functionality. So if you could inject more polyesters in upgradables, I think using recycling polyesters, I think we have good scheme of things there. And like you said, wind turbine blade erosion, if we can do it with epoxies and polyurethane in wind turbine structures. And then, cold spray is going to play a more important role. Can we use cold spray more than what we are currently using? Ductile elements, but if we can move to brittle elements, some of the effort that like Professor Harpreet Singh's team in India is doing, if we can induct cold spray to that, open up cold spray to ceramics and cermets, I think it's a big contribution to opening it up for which for applications which never moved out of thermal spray. I think that will be a great thing to do, and a lot of machine learning, plume data, collection of data, and working with this OEMs and PLC programmers to get a sustainable robot-dominated thermal spray process. I think we have a good opportunity there. And turbine technologies are one that are pushing the boundaries, and we have to keep in sync with that. We need to get more and more material solutions to catch up with those turbine technologies. So those are some of my thoughts. I think we can work on. So with that, I think I'll just briefly go through what I have done in my PhD. I've developed some free-form nanostructures like tubes and rods using cermets and aluminum oxide, using thermal spray and solution precursors, plasma spray. To improve the flowability, I have used spray dryer of these nano powders. Mostly ceramics and nitrides and polysilicide, hafnium tungsten, hafnium carbide. I think we got, we could scale up. All these technologies can be scaled up, and I think with the right talent, I think we could work more closely and collaborate to get things done. My experience is mostly on thermal spray, monitoring diagnostics. I worked with these guns, and we should be able to collaborate. We have a thermal spray facility in London South Bank University, mostly plasma spray, but we could do a lot of collaboration in terms of leveraging each other's infrastructure needs, like cold spray in India and solution pickle spray, plasma spray in University West. So I think it's we have a good talent to work together on some of these technologies, and we could develop a lot of bumper to bumper solutions, like from selection of powders to cermets to gas selection parameters, and how to deploy it on a high level coatings. I think we could work more closely and get things done. So with that, I would like to end this presentation. I think it's running about 45 minutes, and yeah, so we will work more closely with this networks and technologies and with this right talent. I think it's time to work together. Thank you so much, Professor Saurav and DSM Network, for me. It's been a great experience.
Thank you so much, Vish. That was quite comprehensive. You basically mull all your industrial experience like a condensed sort of a factor. So let me first begin by congratulating you and thanking you for this extensive presentation. There was a mention already in the chat box from Abneesh also giving his congratulations and acknowledging that the talk was really splendid. So before I take up the question, if there's any immediate question, if somebody would like to ask, then you are welcome.
Saurabh, Harpreet here. It's just like I just appreciate Dr. Vish for giving a very nice perspective from industrial point of view, and I really look forward for this collaboration maybe with him because even brittle materials. Yes, it's also my dream that somehow we can make it happen through cold spray, and maybe we can work in future. So it's not a question; it's just like appreciation for Dr. Vish, and I wish we can have some collaborations in the future. Yeah, in fact, we are open for anyone from DSM network for any kind of collaboration. Yeah, thank you.
Yeah, one line of thinking I had, Professor Harpreet, about when I was seeing these talks yesterday, and when a question was raised about silicon carbide, which was actually a PhD topic in itself. I was thinking about some of the concepts that can be imbibed from a precision manufacturing, subtractive manufacturing perspective, where every brittle material is supposed to undergo this so-called brittle ductile transition.
Hmm.
Can play around with the strain energy that is released in the duration of the high strain rate of cold spray, and if that can
Yeah,
be, I think then we can achieve ductility in a
yeah,
limited time domain. So there are some thought process which I had in my mind yesterday, and I thought maybe we should develop these ideas further. From, I mean, that was the
yeah.
objective of the event.
Right, right.
Learn
Yeah,
ideas.
even there may be another route that we apply some maiden materials and then have some secondary processing to convert them to these kind of phases, right? So yeah, I mean we will love to have some kind of collaboration in future, and that's the beauty of this activity that
No,
we are opening up.
very much look forward to collaboration. Sure, no problem.
Yeah.
Um, yeah, thanks a lot for that. So one question which Avnish asked, is it possible to do in situ thickness measurement of the coating while it is being sprayed?
So yeah, we have tried laser technology for that. Basically, it it if there is a high temperature involved, for example, cold spray, it's very much possible. As it builds up, you send an optical light and you could do it. But when the temperature gets higher, it will actually, the phonons and the scattering of the heat waves, it gives a erratic reading. So that's why I said there is electromagnetic waves can still be used, and there is a lot of promise there to build that kind of thing for thermal spray. But for cold spray, yes, we can use optical, like blue light. If you have heard of that commercially available GOM, GOM, it's basically a optical camera that can fit into the coating cell, and you can measure it real time. So
Great. So Vish, I have some questions, just like how I asked Avnish, not
yeah.
related to technical purely, but for the ECR community. For example, if somebody asks you, where would you suggest to go after PhD, industry or academia, what would your reply be?
Okay. I think, see, with the so when I graduated 2007, I was actually looking to to build up on robots. But how robots is used in thermal spray. I was fascinated with that. If you look at it, the situation now after 14 years, 15 years, I think there's a lot of this startup thing and consulting. So I think academia can bring more startups in thermal spray itself. A lot of the this aspiring early careers can use academia as a jumping board to spin-offs and consult and do a lot more thermal spray innovation. being part of academia. I think thermal spray industry is still stressful in the sense that if you get in there, you might end up not able to do a lot of research. But I think if barring a few corporations, I'm not talking across the board, but I think academia is still a peaceful place to innovate and contribute to the thermal spray world.
Okay, great. And one maybe follow-on question on that, Vish, is, I mean, although you worked in GE, but can you envision your career growing in the same manner, working in an SME? Like, what sort of challenges an engineering professional would have faced working in SME compared to a larger organization like GE?
I think so. Typically, if you look at small and medium scale industries, are obviously the growth is going to be a lot more faster compared to the big corporates. Because if they look at the overall goal of an aviation company or a power generation company, they are selling turbines and their technologies, and thermal spray and materials engineering are such a minuscule portion of their profession, is that you might end up as a support profession. I mean, it's not bad, but on the other hand, if you work for a small scale industry, whose whole bread and butter is thermal spray, I think there's a lot of opportunity to grow. To start with, yeah.
There is one question from Rakesh in the audience, which is about your subject domain expertise. What are the current robotics technologies used in industries to achieve micro and nanoscale accuracies in thermal spray?
I think I would take this question as a bit, more specific, but I mean, in terms of micro and nano, if you are talking about feedback systems, it's basically, if you can end up using the robot for faster motions, you could end up even getting thicknesses of the order of semiconductor level, like 1 microns. I'm not talking nanometers, but 10 microns to 1 micron. We could go there, but in terms of usage of thermal spray in semiconductor industries, I think it's still not there because it's still a precision industry. But there is a potential to scale up this nanometer level coatings in that field as well. If we have like mirror finishing, right? If we can coat something on a mirror finishing substrate with that scale, I think there's a lot of things to do there.
All right, Vish. I think if there are no more questions, then I'd like to thank you.
Thank you
for sharing your valuable time and insights into industrial landscape of thermal spray and sharing those, bullet point which are crucial for helping SMEs and industries to grow from academics, which is the expectation. And as Professor Harpreet was saying, I mean, we need to continue to grow in this area by working collaboratively together across borders if required.
Yeah, sure. Thank you.
Thank you. Thank you very much.
Wish for that nice presentation.
Thank you.
So we have with us the ECR joining from the US, the final talk for the day for the Thermal Spray Week. John Saputo, and he is actually working very closely with Professor Sanjay Sampath. And there was a small bit of turbulence on the timing scales, but I'm glad to see him here, which is again amazing thing. So John has been working a lot on coatings, particularly to improve the efficiency of compression ignition engines. And let us see what John would like to share with us today. I'm sure that working with Professor Sanjay Sampath would already be a nice experience. So We'd love to see and hear his thoughts on the coatings for IC engines. John, welcome to the DSM network.
Thank you. I'm going to share my screen here really quick. Make sure everybody can see that before I get going.
Yeah, go ahead.
Okay, all good. Cool. Thank you for having me. As you said, I'm going to talk about coatings for increasing the efficiency of compression ignition engines. Seems to be a bit of a different topic from our last speaker. This is a bit more research-based, maybe connects a little bit less broadly to the community, but it's still potentially an interesting direction to move in terms of the industry. So this work is partially done in collaboration with the U.S. Army Combat Capabilities Development Command Ground Vehicle Systems Center, which is a mouthful of an acronym. But they're the people that are doing the engine testing from a lot of the things that I'm going to show in this talk. And there's a couple of folks there, Eric Gingrich and Mike Tess, that I have listed on the bottom here, who are main collaborators there. So I think the motivation of this is something that I always need to call out first when I give a talk like this. As soon as you mention internal combustion engines, people tend to think of things like cars and buses and trucks, and their immediate reaction is usually something like, why do I care about that? Electrification is going to get rid of all the issues that we have with these things. But besides on-road vehicles, there are a lot of systems out there, like farm equipment, construction, and construction, mining, and heavy equipment, and then also things like marine and naval engines that are generally represent a much larger cost than on-road vehicles. And I'll give some examples here. I'm going to apologize. These are all in American units, everything that I'm about to show. I probably should have thought about putting these in SI, but hopefully this still translates well. As you go down in this list, you increase in cost generally. So something like an on-road vehicle will be on the order of magnitude of something like $10,000. So your car will cost $10,000, $20,000, and maybe something like a bus or a truck will be a lot higher than that. But just for demonstrative purposes, I think this is suitable. As you go down, you approach marine and naval equipment that can often be on the order of $10 million. At the same time, the difficulty of replacing the internal combustion engines in these systems also increases. So that's a hard metric to really hammer out, but I chose something interesting here to look at torque in these systems. Torque is a metric that electric motors generally excel in. So something like your car, which again, sorry, these are in English units, would produce something on the order of 100 foot-pounds of torque. Maybe that's something like 150 Newton meters. And then as you get to the other end of the scale, something like marine and naval engines are producing on the order of 1 million foot-pounds of torque. And it's one of these applications where there just isn't a practical alternative to an internal combustion engine. And at the same time, the environmental impact of these things gets worse and worse as you move down in this list. So again, that's a difficult thing to quantify, but I'm putting this in the cumulative tons of CO2 emitted by each of these categories. So if you look at something like all on-road vehicles in the world produce something like 10 to the 9 tons of CO2. And as you increase, if you go down on that list, you can see it immediately drops down and then picks back up again. And that's just kind of skewed by this, the sheer number of on-road vehicles that exist in the world. So you can think there's probably 1 million times more cars in the world than there are container ships. But even still comparing that, those two numbers, 10 to the 9 for on-road vehicles, 10 to the 9 for marine vehicles, are about the same, which tells you something. So in combination, these first two categories tell you that these things have a longer projected lifespan as you go down in that list. So an engine or a system that costs on the order of $10 million and creates more torque than anything else in the world is going to be really difficult to replace. And at the same time, there's a large need to do that because there's some of the most polluting vehicle systems out there. So I'm going to call it 3 specific things that I think we need to do here. One of them is to make these new irreplaceable systems more efficient. The second thing is modify existing systems to be more efficient. And the third thing is to be able to integrate these systems into some more environmentally friendly areas. So the first example that I'll give is, for a container ship. So this is a Wärtsilä-Sulzer 96C engine. You can see there's people in that bottom image, and these things are the size of a house. I think this specific engine outputs about 7 million foot-pounds of torque, and there's literally no replacement for this thing out there. The second example I'll give is military combat vehicles. So a lot of these things have very specific performance requirements that there aren't a lot of alternatives to. And they tend to have really long lifespans. So this is a vehicle that was introduced in the 1960s that's still in the field today. And you can see that they're constantly introducing these things that rely on these sort of old dirty technologies. And are expected to have very long lifespans. And at the same time, you have things like integrating them into enable systemic benefits. So this is an example of things like wind or solar that produce intermittent power. And you could possibly supplement those things with internal combustion engines, which can ramp up to produce power really rapidly, which is a kind of unique attribute of those systems. So altogether, you're probably not likely to see any of these things have practical replacements in the order of 50 to 60 years. So even though, environmentally friendly green technologies are really popular and have a lot of research going on in them, there's still a deep need to pursue higher efficiency in these systems. So talking about efficiency, it's kind of good to just give you an overlay of the land. What does it actually look like for these systems? So you go back to the 1870s and you can see, Rudolf Diesel's first engine had an efficiency of about 8%. And you go to a modern day high output diesel engine from 2020 at the other end of this and see it's about 46%. So it's interesting, you get about a 40% improvement over the span of about 150 years. Over the past 70 years, you only see an 8% improvement. So that's kind of interesting. Things saturate after about 50 years of improvement and have gone really slowly since then. So if you look at this in the future, what do people expect to happen? And there's projections that in the next 30 years or so, you'll see about a 14% improvement in efficiency in these systems. So considering that there's only been 8% in the past 70 years, 14% seems like a suspicious number. But you can kind of look to how do people in this field project that this will actually work. So there's a couple of things that people look at. The first is looking at efficiency versus peak cylinder pressure. So some of the ideas that people have in this field is that you can just increase the working pressure that these things work at. You increase the amount of work that comes out of an engine, and the efficiency of it will go up. So increasing the pressure has a direct correlation to increases in efficiency, and is projected to have about 1 to 3% impact on that total 14% that I mentioned. So a secondary thing is waste heat recovery, which is projected to be about 3 to 8%. So this is kind of a busy picture, but on the right hand part of this image, they're using a volatile organic compound that's heated by exhaust gases and produce additional power from what would be waste normally. And then a third option is to reduce the thermal losses in these systems. So I'm showing a section of a piston with a thick ceramic coating on top that could possibly use to keep heat in these systems and produce beneficial work. So looking at each of these things, this first option is systemically simple. So it's just a simple modification to the way that you're already running an engine, but because you have these increases in pressure, it's thermodynamically linked to temperature, and you start to push the thermal limits of the materials that are used to make these engines. The middle option here is systemically complex, but readily achievable. And is also thermally limited. So you're not pushing the thermal limits of materials in these systems, but you're limited by waste heat through the hot gas pathways in an engine. And this third option is also systemically simple. You don't need to add an extra system to a diesel engine. You can just modify existing components to possibly gain additional performance benefits. But again, it needs unique thermal insulating materials. So these are three categories of things that can all be enabled by the use of coatings. So I'm going to talk about this reduced thermal losses mostly, and then maybe loop back to this first idea of increased pressures and the thermal limits of materials if we have time. So reduced thermal losses. I have a little subtitle there, or 6 years of TVCs at the CTSR. So we've been working on this idea in collaboration with the US Army for around 6 years now. And if you look at the total fuel energy that goes into an engine, about 50%, 55% of that is actually losses, and 45% of it goes to usable power. Of those losses, about 25% are thermal, 30% leave through the exhaust gas, and then there's some other portion of that that's mechanical frictional losses and things like that. Of the 25% that are thermal losses, about 23 leave the system during the combustion, expansion, and exhaust strokes. And then about 2% of that is heat that's generated by friction. So from the 23%, there's 19% of that that is just goes out of the system as waste heat, conducts through the walls of the piston during those strokes, and about 6% that's potentially usable as work in these systems. So part of the idea is that you can use coatings in these systems to directly increase the efficiency by harnessing that potentially usable energy as work. But there are a couple other things you can do at the same time, like enable the use of alternative fuels, maybe gain some systemic benefits, or keep more of the heat in the system so that it could be recovered by a secondary system like I showed in the previous slide. I'll go over two specific examples of how coatings on pistons can be used in high-performance diesel engines and be used to enable the use of biofuels. So this idea isn't exactly new. It turns out people have been trying to use coatings in these systems since as early as about the 1920s. So this is an example taken from a Scientific American magazine where a guy is literally painting a ceramic on the inside of an engine in the 20s. Back then, this was referred to catalytic coatings, and they were used in early spark ignition engines. And part of the idea was that you could have some wall material, you could apply silica, which is what he's painting on as a slurry coating there, and then put a layer of cerium oxide on the surface. So normally in an engine, you would have some combustion process and hot gas traveling over the surface. In this environment, they imagined that the hot gases would interact with the cerium oxide particles that are on the surface, have some catalytic reaction that would allow the combustion process to proceed to a fuller combustion. So if you look at what they actually measured out of these things, this is a plot of basically efficiency versus the pound of fuels that they put in to the engine per hour. And you can see that the catalytic coated engine was always more efficient than the uncoated engine, and they used less fuel. So it's interesting that back in the time that they were doing this, there's a really poor understanding of how engines worked. And they didn't really, understand the implications of these coatings on these systems. But what they got out of it was that they had lower fuel consumption. They suppressed knock and allowed them to go to higher pressures. Going to higher pressures allowed them to go to higher efficiencies and have increased rates of combustion. But as soon as you introduce leaded gases, which happened, shortly after these were being used, those issues with knock went away, and they didn't really see the performance benefits that they got from going to those increased pressures. So the poor understanding of engine dynamics at this time sort of drowned this out. And there's an interesting aspect of this, whereas you have a silica coating on the surface, which has a conductivity of maybe on the order of something like 1 watt per meter Kelvin, versus the steel or aluminum that's would have been made out of that'd be 40 to 100 watts per meter Kelvin. So it might actually have been one of the first early TVCs that you'd see in the system. So the real first examples that you see of this come in the 1970s, and were given specifically for marine life extension. So these are traditional TVC materials, derivatives of something that would be used in the aerospace industries. And they're used to reduce hot corrosion in these systems by the really impure fuels that are used in marine engines. So this idea is kind of simple. You have a thermal gradient that runs through one of these systems. You put a low conductivity material on the surface, and the temperature will drop. And you'll have a lower component temperature at the backside. It's widely used in aerospace and tried to transition over to this industry. So this is an example of a zirconia TVC that was tested for about 1,000 hours in a marine engine, and you see no real damage. So it was only speculated at this time that this could cause benefits to the thermal aspects of the system. So this is a dirty old piece of paper taken from a Department of Energy report that you see there. It's kind of difficult to spot in here, but I'll call out these numbers that they give, that they projected that you could have a reduction in the heat flux that travels through the wall in these systems, but they didn't actually do any measurements of this. So they did see it successfully suppress hot corrosion in these systems. They didn't really see many failures in the coatings at this time, and they predicted there might be a potential to reduce heat transfer. But there's no actual efficiency testing and no engine performance testing. All they looked at was, did these coatings reduce the erosion rate that they see on pistons? This idea sort of ran off in the 80s and turned into this concept called the adiabatic engine. And part of the idea was that, hey, you could make things out of ceramic inside of these systems. Ceramics can live at higher temperatures, and maybe you can remove the cooling system in these systems, which is this dramatic sort of revolutionary idea. So people took this idea all the way to a platform scale. So this is an example of an adiabatic engine that was part of a Cummins TACOM joint program, where they did remove the complete cooling system from this engine and then coated all the internal components with ceramics and did, platform level performance testing. So this is another example looking at fuel consumption versus load on the engine. And you can see at every point that they test that the uncooled engine is more efficient than the cooled engine, which isn't really a great surprise. But they only saw about a 4% gain in efficiency and a 60% reduction in heat transfer losses, which is kind of interesting. So the interesting thing is that the majority of those performance benefits actually come from removing the cooling system. So you're removing this parasitic loss that normally gets taken away from the engine and not necessarily gaining performance benefits from directly having the ceramic components. At the same time, because they remove the cooling system, the temperatures get really high and you see these issues with lubricants. So the oil on the cylinder liner and things like that start to get too hot and burn. There's issues with durability that you see for trying to replace all these complex components of ceramics. And then the efficiency gains mostly came from, they're removing that cooling system. So in the 80s and 90s, you see people start to look at these things and try and actually gain performance benefits by insulation. So the idea in this time would they would use coatings on the order of 1 millimeter thick, just add them onto existing components to try and augment heat transfer. So what you see is something that happens like this. So this is the surface temperature of a piston versus different crank angles. You can think of this just as different times during the combustion process. And as you go from a thinner to a thicker coating, you're moving from the bottom to the top line. And you see, that baseline temperature slowly go up and up, which ends up being an issue. So what people predicted was that as the surface temperature of the components get hotter and hotter, you're going to slowly degrade combustion by heating the cool intake gases that come into the system early in the cycle. So you can see this performance testing again shows interesting results that using a thinner ceramic actually performs better than a thicker ceramic. So this is telling you that even though you have a higher insulation capacity from these thick ceramics, that they perform worse. And that's partially due to the reason I mentioned of the heating of the intake gases. And so it's interesting, there's theoretical predictions about this made as early as the mid 80s, where people are showing that, these thinner ceramic coatings, as you move to higher frequencies, could possibly perform better. So overall, this sort of period in time can be summarized by there's degraded performance from thick ceramics. The potential to use thin coatings has some benefit. And then because people were using these thick brittle ceramics, there were some pretty severe durability issues. So that kind of leads you into the present state of thinking in this field. From about the 1990s to now, people have had this idea that you can use thin coatings to gain performance benefits in these systems. So I'm giving an example of maybe a 30 micron thick TBC that comes from Toyota. That's not made by thermal spray, but made by a different process. And these coatings are generally something like temperature swing or thermal swing coatings that are used to reduce conductive heat transfer in these systems. So just to explain that idea, if you look at the combustion gas temperature as you move through a cycle, we have intake, compression, combustion, and exhaust. You can see it kind of rapidly swings back and forth from about ambient temperatures to upwards of 1800 Kelvin. If you put a metal wall in this system, so it's just a normal traditional piston, you'll see that it's about a steady state temperature. So there's a couple of interesting things that happen here. So there's a small portion of this during the intake cycle where that wall is hotter than the gas. So that tells you that the heat is going to transfer from the hot metal in this surface, in the system, to the cold intake gases. And that during the compression and combustion strokes, there's going to be a huge temperature gradient going the other way. So heat transfer is going to go one way and then immediately turn around and go the other. So if you put a ceramic, this is a 500 micron thick TBC in these systems, you see, a sort of exaggerated thing happen here. So during that intake cycle, the difference between the hot surface is a lot larger, and this is now smaller. So those heat transfer losses that you're seeing during the intake cycle get even bigger. Ideally, what you'd want in this system is something that looks like this, something that has a low mean temperature, but then quickly spikes up to meet that combustion gas temperature at every point during the cycle. So a nice metric that you can look at is just this temperature jump. Ideally, what you want is a really big temperature jump and a low mean temperature. So this is sort of the idea that everybody's been pushing for in these systems for the past decade or so. And a lot of this involvement is happening all over the world. So there's a few programs in the US working on this ourselves, some people at the University of Madison, Wisconsin, and John Deere, Clemson University, and Daimler, and Hughes Research Laboratories. In the EU, there's a big push for this as well. There's some University West, and Scania, and Volvo trucks. There's the Eagle Consortium that's kind of all over Europe working on this. And then there's some work in Asia as well. So Toyota and Hino Motors in Japan. In India, there's Cummins and Indian Technology that have been working on this as well. So what are these coatings is probably the next thing to address. A lot of them are traditional TBC derivatives. So you have something like a YZ top coat and a superalloy nicrally bond coat that are used in most applications, most examples rather. And then you have things that are, some sort of derivative of that, like functionally graded materials. You have suspension spray coatings that people are working on with this as well. And then sort of alternative TBC materials, things like gadolinium zirconate that people of Clemson University have tested. And then you have this whole class of things that I consider novel coatings, these thermal swing materials. So this is a picture of the material that we've been working with that I'll get into detail a little bit about, but they're generally low density, low specific heat materials that are designed to have that temperature swing effect that I talked about. So I think two of these are plasma sprayed TBCs. One of them is an anodized aluminum coating, and then the other one is a slurry coating. But they're all sort of tuned to have specific thermal properties and aren't derivatives of traditional thermal barriers. So if you look at material selection for what's needed in these systems, I think this is a pretty good study. This is a guy from Wayne State University that did a bunch of simulations, conjugate heat transfer simulations of an engine, and just used a huge sweep of thermal properties to see what would be most beneficial in these systems. So I'm plotting thermal conductivity versus thermal diffusivity in these systems, and you can kind of see that as you go down to the right, the predicted efficiency gains in these systems goes up. So we're pretty lucky at the CTSR. Our lab has been around and measuring thermophysical properties of sprayed coatings for a long time. So I've got a list of about 13,000 measurements of actual sprayed coatings that we can look at. And you can take this same plot, conductivity versus diffusivity, and overlay that onto this guy's efficiency plot. And you can see that there's a certain range down here that falls into this green category that's readily achievable thermophysical properties of a sort of traditional coating that we want to look at. So these specific materials are these 6 things here. So they're all magnesial-luminosilicates. The 3 examples that I'm giving are mullite, which is has been used in the aero industry, that steatite and cordiorite, which are less commonly used. They're all sort of really, well, 2 of them are really brittle, low conductivity, low density ceramics. And then the other 3 of these things are actually composites that were developed using these brittle materials, sort of toughened with zirconia. So we know that these have the properties of interest that we want, but we want to know, do they actually perform an application? Are they suitable for an engine, like before you put them into an actual combustion engine test? So we came up with a rapid screening methodology to sort of figure out, do they behave like we want them to, and are they suitable materials? So we're just using an HVOF torch and this sort of spinning shutter. It's a steel cylinder with a hole in the center. And it sort of rips around the coated sample in the center and gets rapidly shocked by, this HVOF torch. So we're able to do this at frequencies between 10 and 1,000 RPMs and push the temperatures between 200 and 600 C, really making it relevant to these, the conditions that you might see in an engine. So we can do this test and record the surface temperature transients that involve using a thermal imaging camera to really, understand what's happening to these coatings in these systems. So the data that you get out of this looks something like this. You get each one of these cycles sort of rapidly swings back and forth. This is 10 minutes of continuous exposure, about 1,000 cycles, and it's useful for both traditional TVCs and these novel materials that I was talking about. You can zoom in on one of these little sections and see what happens during this cycle. So the steel is the black line, zirconia, traditional TVC, is the red line, and there's two interesting things that you get out of it. The first is that temperature jump that I was talking about before. So for steel, it's about 21 degrees, and that baseline temperature is about 170 C. For zirconia, that temperature swing is about 40 degrees. And the baseline temperature jumps up, which would be bad because it would degrade the thermodynamic efficiency of an engine by heating the intake gases. So if we look at one of those, the most beneficial materials that we predicted from the other work that we talked about, you can see this is cordierite, that the temperature swing is about double what you see from anything else. It's about 90 degrees, and the baseline temperature is about the same as the uncoated steel, which is good. So by our lab test, this should perform well. And you can kind of lay this out with, theoretically how some simple heat transfer correlations work. You could look at that thermal swing versus thermal effusivity, which is defined as the square root of conductivity, density, and specific heat. And it should trend like this, inversely proportional to that temperature swing. So that's exactly what we see. It works that way for a broad, swath of materials. So these things should work great in these systems. But you still need to get these things onto a piston. So these generally look like something like this. You want to move a spray torch across this surface, keeping it normal the entire time in order to develop a uniform coating across the surface. So these pistons are something like 120 to 150 millimeters in diameter. And they're huge. So doing metallography on these things, trying to understand if you have the proper microstructure across every location on this piston is complicated. We came up with these little strips that sort of fit on this component, mock geometries, that you can just quickly destructively test it to figure these things out. And allows you to rapidly develop that tool path to get optimal coating microstructure and thickness. So when you're spraying these coatings, looks something like this. We're generally rotating these parts and traversing the piston, traversing the torch along the center line, keeping it normal the entire time. So if I look at one single feature on here, it says bowl edge is what this part of the piston is. It generally has a specified dimension as fine as about 30 microns, which is kind of difficult to do with some spray processes. So as you receive this, it looks something like this. And the first iteration of developing the coating tool path on top of this looks something like that. You turn that 30 microns into 500, and it's actually kind of terrible for these systems. So using those strips that I show on the left, you can iteratively go through this procedure of kind of a brute force optimization, making the coating more uniform and more uniform as you go until you get a uniform coating across the entire profile. So that's really important to do because the bowl geometries in these high performance diesel engines are often designed using computational fluid dynamics. And people often predict that, deviations on the order of hundreds of microns in these systems can cause a larger change to the combustion process than the presence of the coating, which is kind of interesting. If you go back and look at the literature, you'll see a lot of examples of coating variabilities across the piston profile that are varying by as much as 0.5 millimeter, which would make, decoupling the effects of the change in bowl geometry versus the coating materials in these systems basically infeasible. So just to give you a brief summary of the work that we've done at CTSR with this, we've kind of gone through this cycle of doing these laboratory tests, developing pistons on coatings on piston crowns, and then doing single cylinder performance engine tests, and then using that as a feedback loop to continually develop better and better coatings. So doing this, we've tested about 20 TBC varieties from coupons all the way to engine test, which is kind of interesting. So the first work that we did with this was just looking at traditional derivatives of aerospace TVCs. So if you look at a baseline engine, are about 48.5% efficiency. The first coatings we put in are these blue bars, and you can see that that drops down. So we're looking at about 185 micron thick coating and 325 micron thick coating that cause these performance degradation, which is kind of interesting. So when we first saw this, our first takeaway was, hey, these coatings are kind of rough. They're in the aspirated state. You got a picture on the right, has that nice matte finish. Why don't we polish these and put them back in the engine, which is on the left, on the right. It's nice and shiny now. We know that this is done quite often in aerospace to reduce any sort of turbulence that might happen across the surface of these things. And you do that and it turns into the green bars on the right. All of a sudden you see this performance degradation turn into a performance benefit. And that performance benefit is proportional to the coating thickness. So as you go to that 185 to 325 micron thick coating that's polished on the right, that increment increases, which is good. So we're going, looking at the surface of these things. It's a aspirated roughness of about 12 microns to polished about 6. So you can kind of see that it starts out really kind of chaotic and random, and then as you polish, it turns to this nice plateaued surface with some pits across it. So we can clearly correlate that surface roughness effect to this performance in the engine, which is interesting. So our next thought in these systems was, hey, can we make this even better by making that surface even smoother? So the aspirate coatings, if you look at them in a SEM, look something like that. They're totally chaotic and have all these really small scale features. So as you polish it out, you can see this, and you still do see pits on the surface that we thought may have some interaction with the combustion process. So to get rid of this, we decided, hey, we can just tune our process variables, spray a dense thin coating on top of that, and seal all of that up. So apply this dense sealing layer on top that's that portion of that TBC, and at the same time put a whole lot of work into trying to make the there's a metallic phase dispersed in that to toughen the ceramic. So we can try and make that more homogeneous. We can get better control over this uniformity of the thickness of the coating across the piston, and it gives us better control of properties at the same time. So all this kind of came together, better control, better understanding. We should have better coatings that come out of this. So our original coating looks something like that. You have all these big open surface pores, you put the sealing layer on top, and they all go away. Everything looks great, right? Except for you do engine performance testing with this, and you see no change in the efficiency. Which is kind of interesting. This story is going to get a bit repetitive, and I'm going to say the same thing like 6 times in a row. We've tried a whole bunch of things and seen really similar results. So our thought from this is that we have this dispersed metallic phase inside of this. A diesel engine is a whole lot like a candle. If you look at this is an optical engine test, you can kind of see something in common here. You have a lot of radiative heat transfer that's emitted from these things. It comes from hot gases, your particulates, soot suspended in this sort of dirty diesel flame. As those soot particles get hot, they emit radiation, and they emit radiation kind of like a black body. So if you look at the spectral emissions that come out of these, there's a peak between about 1 and 2 microns that were the expected maximum radiation. Radiation would come out of these things, taking the adiabatic flame temperature of a stoichiometric mixture of diesel fuel and air. If you look at the coatings, they have this 5% added metal volume fraction. If you look at the expected optical properties of these things, you can see that the reflectivity, which is a decent metric, analog to the absorption of radiation in these systems, is about 20%. If you look at a traditional thermal barrier coating, like a pure ceramic coating, so those are about 70 to 80% reflective over that spectral range in this kind of a system, which is interesting. So we're taking this, by adding that metal, we're toughening it, which is great. And we're, not changing the thermal conductivity or anything like that, but the propensity for radiative transfer is, going up by a factor of about 3 just by adding that metal into the system. So our thought was, maybe that's bad. Maybe that's what we should be trying to take down in these systems. So again, you can take a piston with 5% metal volume fraction like we tested before, remove that, and kind of tune the thermal properties, the conductivity of these systems to be about the same, and do performance testing, and you see absolutely no change, which is kind of interesting again. So we decided to go from this to the thing that everybody's been driving towards in the new system, which is these thermal swing materials. This is that cordierite zirconia composite. the same thing that I showed you, the blue, nice temperature following coating that we had before. We know that this performs in laboratory tests by all metrics about 2 times better than YSZ. It's predicted to fall into a range where it should get about 2% change in engine efficiency based on all these simulations. It's got a conductivity of about half zirconia. So by all metrics, this thing should be a good engine coating material. But we did also 3 variants of thicknesses in this. So we did about 150, 180, and 370 microns in case that's an issue. We did see that earlier. But for all of these cases, we see absolutely no change to engine performance. So our thought with this was maybe it's the roughness. We already determined that that's interesting. So you look at the zirconia coating. I said it's about 6 microns RA. Here I'm showing it's 5.9. On the right, this is the Cordiorite zirconia piston. It's 9 to 10 microns. So it is a bit higher, and maybe that's the reason. So we got new powders, developed a new spray process. Using a slightly denser coating, you can get lower surface roughness. So I'm showing we were able to knock the final aspirate pistons down to about 6 microns RA and put this in an engine again. And again, you see absolutely no difference. So our thought process went to something like, hey, maybe the coatings actually influence combustion in some other way. So normally you have something like this complex bowl geometry, you have fuel flowing and air mixing into the system at the same time, and that maybe there's some other interactions that we're not thinking about happening in this system. So we decided to make pattern coatings. You can only coat this outer edge of the piston where there's little air fuel mixing happening, little of that interaction with combustion process, and then do the exact opposite, do this inner portion. But when you do this, something miraculous happens. Absolutely nothing. So it's beginning to be a bit of a repetitive story here that you don't see a whole lot of change in efficiency in these systems, basically no matter what you do. So this is the sort of a high performance diesel testing that I was talking about before. We did this to death. About 20 engine tests performed using thermal swing coatings, patternation, zirconia coatings, changing the thicknesses, using different sealings, different microstructures, radiation coatings. There's a lot that I didn't even talk about in here. We tested coatings that were up to the millimeter scale in thickness. Didn't really see any changes from any of this. We did things that were just, low conductivity metals, and then some instrumentation testing that I'll talk about a little bit later. And then went back and did a bunch of uncoated engine tests. And what you end up seeing is that the range of variability that you see in these systems is kind of huge. So we're seeing about 47 to 48% change in just the uncoated tests, which is outside of the variation that you're seeing in the tests that we're using with all these different TDCs. There are some things that lie outside of that range, some things that are below and some things that are above, but those benefits are rather small. So at most they're about 0.5% that you could potentially gain from doing this, but it would be really difficult to actually get everything tuned exactly right to do that. So you can go to, instead of getting direct performance benefits from these things, into enabling different technologies. So one of those big things is biofuels. So this is work that we did with Clemson, and it gets interesting. Use a lot of these same coatings and compare it to a baseline engine, and you immediately just see the performance go up. So in these systems where there are current limitations, so you can see that just the baseline engine performance in this is about 44.5%. For that high performance diesel engine, it was 48%. So you're already starting lower and there's more room to move upwards, which is kind of interesting. And you can immediately start gaining benefits from that. Which is great. So in these systems, there is this direct significant benefit that enables these biofuels, which have issues, to combust and perform like a more traditional engine. So increased efficiency directly, kind of questionable. Use of alternative fuels, absolutely. Systemic benefits and waste heat recovery, kind of questionable. So I think, I started a bit early with this. If you guys want to keep this going, I can talk about the last section of this, or I can cut it off now. Saurav, I don't know how you feel about this. You're sort of leading this session.
What's that, John?
So I can keep going with this for a little bit. I know it's 9 o'clock. I don't know what time you guys wanted to end this. I could probably ramble on for another like half hour or so if you guys want me to.
Perhaps, yeah, can do about 15-20 minutes.
Sure.
Yeah.
Okay. So, I've sort of gone through all of the potentials for reducing thermal losses in these systems, at least in terms of coating a piston. The other thing that we can talk about quite a bit is what people in the engine community actually want to do. So there is this prediction that you could increase pressures in these systems to directly gain performance benefits. And that you run into materials limitations by doing that. So I can talk about how coatings can actually enable you to do this and possibly alleviate some of the issues that you see with this. So increasing cylinder pressures is interesting. We already went over, you increase pressure and the increment in efficiency that you have is linear, but you run into big issues with temperatures. So these are generally thermally limited systems to begin with. So I'm giving two examples here. The top one is a marine engine. Where you see that when stuff gets too hot, you're literally just burning away the piston material. And the bottom example is an automotive head with a valve in it where things get too hot and you burn through the valves. So there's a lot of materials limitations in terms of temperature in these systems. A lot of them are made out of something like 4140 or microalloyed steels, at least in the high performance diesel engines. Automotive engines, something like cars, are usually aluminum silicon alloys that operate at much lower temperatures. But these things are steels that are meant to operate on the range of about 300 degrees C. So as you increase the temperatures in these systems, two things happen. One is that you start to oxidize. You have hot corrosion in these systems as well, but we won't really get into that. And then the second thing is that the tensile strength or the yield strength of these materials will start to bomb out around 400, 500 degrees. So there is a range here where the mechanical properties of these systems aren't really degraded enough to stop them from performing in these systems, but they do rapidly oxidize, which is the issue that people have been running into trying to go to these higher pressures in these systems. So that's sort of the thing that we can drive down and hope to get away, make go away with coatings. So in these severe operating conditions, you really need some metrics inside of these systems outside of things like efficiency that we were looking at before. So the way you get that is, so this is work that we did using telemetry pistons. Each one of those red lines that I'm showing on this sectional CAD model of a piston represents the location of a thermocouple implanted inside of a piston. So this is what this thing actually looks like, is some electronics that are sort of screwed on to one edge there that transmit data. And then you can see at the bottom that silver line or thermocouple leads that are taped to go to this telemetry system. So the first work that was done with this was just looking at, an uncoated piston. There's no coatings. We want to just know what happens when you sort of push these pressures and temperatures in these systems. So you don't actually want to increase the pressures in these systems for an engine that's not built to do that, but you want to go to the temperatures that are relevant for the next generation of engines. So the way that our collaborators did this is work from the Ground Vehicle Systems Center, was just to reduce the oil cooling that goes into these systems. So you can basically just shut off the oil that normally cools the piston and see how the temperature gradually climbs up. So they're able to push things to about 515, 520 degrees Celsius, which is on the order of what people are expecting these increased pressure increments to push temperatures to in these systems. So that's great. You can take a piston out of this, put an uncoated piston in the system. They'll go in looking something like this and come out after about 50 hours looking something like that. So this is with no coating. This is just a bare steel piston, and they tend to rapidly oxidize. So you can look at, this is a cross section of the piston showing different micrograph locations across that surface. A to L are the outside, left to right edges. This is the intake and exhaust side of the piston. So the intake side is expected to be a little bit cooler. That's where the cold air is coming into the system, and the exhaust side is expected to be a bit hotter. So where all the combustion gases are leaving. So I'm showing temperature results from that thermocouple instrumented piston. You can see that pushes up to maybe a maximum of about 520 degrees on the exhaust side. And I'm showing the oxide scale that develops across each location. So look at some of these locations look kind of terrible. There's two specific that I'll go into detail here, L and J. Start with L because it looks the worst. But it turns out L isn't actually oxidation. It's not real degradation happening in the system. So if you look at it, you can do elemental maps of this and figure out that it's mostly comprised of calcium, phosphorus, sulfur, magnesium, aluminum. So these are impurities in the fuel and oil, it turns out. So these are just combustion deposits that build up on the surface of the piston over time. So this is inevitable. This isn't something that you're going to be able to get to go away with the coating. It's not necessarily something that happens specifically because of the high temperatures. It's just kind of, the way of life in these systems is to have these buildup, this kind of buildup happen over time. So you can see the oxide scale here is actually pretty thin. It's this yellow map. It's about a micron thick in this region that it looks to be detrimental in. So that's not actually that bad. If you look at that other region that I called out, is this one, where you have about, maybe a 20 micron thick scale that forms, which would be a scale growth of about 0.5 microns an hour. And that number might seem small, but you got to remember that the service lives of these things are about, order of 10,000, 100,000 hours or something like that. So that kind of scale growth for those sorts of service times would be absolutely detrimental to these systems. So you'd be looking at burning through the entire piston by the time that this thing got to see its service life. So this actually, this scales at different positions too. So I'm showing this in different temperatures that we measured for the intake and exhaust scale side. And it, would be better or worse in some of these regions. So the first idea is that you can just slap an oxidation resistant coating on top of these things. So that's what we did. So this is a nitrile coating that performs really well in these high temperature oxidizing environments, and put it through that same degradation test, and it'll come out looking something like this. You compare that to an uncoated piston, and it actually looks kind of great. You can kind of see it's still shiny. It does have some charring around that outside edge. You can see where the air and fuel combust on the surface and those little periodic arrangements around it in a circle. And you can look at cross-sectional micrographs of this after testing here on the left, and you don't really see any degradation to the system. It's after 50 hours of testing at 519 C. And you do some surface imaging of this. You can see some of this soot buildup along the outer periphery of the piston. That's what you're seeing, those black spots that are sort of in that left micrograph. And the right, you see a higher magnification image, and you can see the finishing marks on the surface. Those finishing marks come from when we're polishing these things to make them smooth so they don't interfere with combustion. And it's great that you can see them because it's telling you that not a lot is happening on the surface of these things. You can directly compare this, the nitrile coated and the uncoated piston, and you see none of that oxidizing damage that you would see in the system in the uncoated piston, which is great. All those issues just kind of go away. So this really enables you to go to these higher temperatures in these systems and not have too many issues. So there's still other benefits that are possible to gain out of this. Again, going back to these telemetry pistons, you can put a thermal barrier coating on top of these things now and look at how does the temperature actually reduce in these systems. So the blue curve in this is a TPC coated piston, and the red curve in this is an uncoated piston. And you see a couple of interesting things. So first, you notice that the temperature is reduced for basically every condition that we test in this. And a temperature reduction in these systems is thermodynamically related to a reduction in heat transfer losses. So you can do some basic math, and it'll tell you that you have about an 8% reduction in heat transfer in the system, which is interesting because in all of the engine tests that we do, you don't see any performance benefits. So what that tells you is that even though you're reducing the heat transfer through the piston by 8%, none of it goes to work, which is kind of interesting. So it tells you it could go one of two places. So the first is that it could go out through the exhaust gas stream and not be converted into any useful mechanical energy in the system. And the second thing is that it could leave as heat transfer through other parts of the engine. So either it's lost to the head or the valves or the cylinder wall, or along the hot gas pathway in the exhaust stream. And the second thing that's interesting out of this is that you see about to get equivalent temperatures, 60% reduction in the oil cooling that's needed, which is kind of interesting. So you could, reduce the pumping losses that go into the oil cooling system, or another option for this would be to just, have the TBC and let it run cooler, and your lubricants would last for longer. both of these are kind of interesting options and could enable systemic benefits in these systems. And the final thing is that if you're worried about the temperatures in this, you're worried about things like hot corrosion and oxidation, you could basically do nothing, run with the same oil cooling flow rates and have the temperatures drop significantly where the mechanical properties of the alloys that you're using are still great. And you're significantly, reducing any propensity for things like oxidation or premature mechanical failures due to, a degradation in the yield strength or something like that. So I think that about wraps up everything that I have for this. Hopefully I managed to fill up this time from starting early and take any questions that you guys have.
What happened, John?
Sorry, I said I think that about wraps up everything that I've got for this. I can take any questions that anybody has.
Oh, okay. So your computer got hang, it seems. Right. Okay. So that concludes the Spray Week talks with the final talk delivered by John. If there are any questions, then people are very welcome to ask you directly. Maybe I'll just ask John, this question was raised also to Professor Sampath. In the wake of growing importance of hydrogen and battery sort of engines, can some of these coatings be repurposed in those application areas?
Yeah, so alternative fuels is, I touched on this with biodiesel earlier and showed how you can get, by using a coating, you can get direct performance benefits from biodiesel. So there's other alternatives, like, compressed natural gas is used pretty commonly in these engines. And as well as, hydrogen is really desired as well. In both of those systems, you're thermally limited in the same way that you are with a traditional diesel engine. So if you want to press those things to higher performance, you'll have these same issues. And this translates really well between those things. Even running it, just hydrogen as a fuel, the temperatures do increase. And there is some speculation that in a dual fuel engine or something like that, you would run into these issues. So all that does directly translate to that.
Also, John, you showed one of these slides where you were measuring the polished roughness and so on.
I'm sorry, I was measuring the...
In one of these slides, you were showing the roughness, the polished roughness of the surface. Obviously, it is established in tribology and in wear fields that roughness holds importance in governing the friction coefficients and other attributes related to tribology. But has there been an impediment in that sense that, like, when you have gotten some parts and you have coated them, do you come across this barrier that you need to significantly smoothen the part for certain application, such as IC engine, where roughness could play a key role? And if that is the case, if you have deposited a certain kind of coating, have you looked into alternative technology other than polishing to finish these coatings?
So roughness has kind of been the bane of our existence in these things. So as soon as we found out, I forgot what slide I showed that on earlier. I'll go back to that really quick. So this is our first work in this. So we found, we're starting with a 12 micron RA and we go down to about a 6 after polishing it. And I didn't really get into how do you do this. So, in industry, there's a lot of different things people do. Some of this is just, called blending, and people do it by hand. So that's literally what we did. This is silicon carbide grit paper, literally smoothing this surface out by hand. So other things that people will do is, use a robot to do the same thing, or they'll use, media tumbling. So all three of those things kind of accomplish the same goal. and would be suitable here. I don't know if you're talking about other things, like you could try and use the process maybe to reduce the intrinsic roughness of the coatings.
Yeah, no, actually I mean, I'll probably say here that actually what I was trying to primarily ask is, how do you achieve homogeneity in getting the same roughness across a free-form shape of a coating?
Yeah, so I think, there's a practical aspect to that. You try and optimize your toolpath to make sure that you're depositing things the same everywhere. In this sort of complex geometry, there's a lot of like turbulence in the spray process that results in the microstructure being a little bit different as you go region to region. I kind of just hand wave and say, hey, everything's the same. A lot of people, you look at any of the literature, that's just what people tend to do. When you are traversing the torch across this area, you're looking at really small feature sizes. I mean, they're not small on the micro scale like you were talking about at the end of the last talk, but they're on the millimeter scale. That sort of 30 micron radius that I was showing and things like that are really hard to control those sorts of features on. Because we're polishing this in the end, the starting roughness doesn't matter a whole lot. So it starts off maybe 10 microns here and 6 microns on this flatter area, maybe 7 microns on that flatter area. By the time you're done with it, it's all 6 micron RA. But you can try and get those things as uniform as you can by optimizing the torch toolpath and things like that.
Great. I mean, I actually saw recently one thesis that I was reading coming out from Indian Institute of Technology, Kharagpur, where what they did actually is they carried out thermal spray coating on hard surfaces, and thereafter they carried out some precision manufacturing operation on it, introducing particularly the abrasive float finishing polishing process. And one of the argument they made in the thesis was, if because polishing is a force controlled process, you cannot afford to go higher in the forces in anticipating higher material removal, because if you do that, the coating might delaminate. So there's a threshold force in polishing that you need to control.
Yeah. Okay.
Very sharp corners and parts like that, this might just peel off the coating completely. But yeah, good, great. So it seems there are no more questions, John, and I think you have done it splendidly, both with time and with the content, and on a relatively short-term notice that was given. But kudos to you and to Professor Sampath for carrying out this marvelous work. And that concludes our thermal spray week, actually, with your talk.
Good.
So,
thank you for having me.
Thank you once again for this. And yeah, I mean, basically we are now coming to an end of the thermal spray week, which has been a splendid weekly journey to cover the pioneers from all across the globe, and the final day, which was really special because we then got to hear our early career community as well. So we look forward to bringing more such events. Right now we did thermal spray this week, but we would be also doing physical vapor deposition and electrode deposition technology to say as an example. And the hope is that by doing this kind of networking activities, we can accelerate the collaborations between various researchers from different parts of the world, and also facilitate mentoring and also career building opportunities for the early stage researchers. And in the process of doing so, if there's any academic individual that you identify that you think you would potentially like to work with, I mean, you can directly contact that person and you can directly get to know their research and so on. So in a way, we are very delighted to be facilitating that platform. So on that note, I'd like to now conclude officially and formally to say that the event organized by the EPSRC DSM NetworkPlus for this thermal spray week has now come to conclusion. And if there is any final thought, Pamela, in terms of any feedback or anything you would like, then please feel free to say that.
Feedbacks, and I'm sure all this work will contribute to the DSM community and interaction and engagements. Thank you so much. Thanks a lot.
All right, so let's stay in touch. Be a good subscription channel on, there's a subscription channel on YouTube for the EPSRC DSM, and also there's a dedicated network website. So please stay tuned.